Ladies and gentlemen, thank you very much for giving me the opportunity to present my talk, a new way of doing adaptive optics with refractive phase modulators. My name is Stefan Weber, and I am the CEO of the startup company Phaseform. We are a relatively young company. We have only been founded 1 year ago as independent startup, but our technology has been in the making for much longer, since 2014, at the chair of micro-optics at the Department of Microsystems Engineering of the University of Freiburg. We are addressing a fundamental topic in optics. How do you compensate for dynamic aberrations? How do you image pebbles on the bottom of a pond, like we see here? Is there a way of optically removing the water? Isaac Newton thought that would be impossible, even with a perfect optical instrument. He said, the star's trembling motions are too quick and confused to be perceived severally when he talked about the atmosphere. It turned to be possible after all. Adaptive optics has celebrated enormous successes in astronomy. So to today, that nearly all information we get from the universe comes from ground telescopes with sophisticated adaptive optics. Inspired by that success, over the past 10-15 years, microscopists have started to tackle their own sources of aberrations using adaptive optics, therefore developing more and more complex optical setups. But the sources of aberrations are different. They have diffractive index mismatch between the layers of the sample and the objective, and you get spherical aberrations from that. And you have also variations in the shape of the refractive index of the sample themselves that leads to complex high-order aberrations. And it has been studied extensively that only with AO you can study cell processes deep inside the tissue with the highest possible resolution, as shown here for that subcellular image of a nerve fiber layer of a mouse retina. Contemporary AO microscopy follows a similar optical design than in astronomy. So you have the distorted wavefront, is measured with a wavefront sensor, and it's corrected by the means of a deformable mirror. And that is actually difficult to implement in a microscope, because microscopes work in refraction, not reflection. And we take a new approach to this. We have a high-resolution continuous surface refractive element we call deformable phase plate, and that allows us to create a microscopic AO system completely inline. And our core technology that allows that we call deformable phase plate. It is transmissive. The actuation is inside the aperture. It is non-polarizing, virtually diffraction-free, and can be produced using MEMS processes. How does it actually work? I'm showing here in a quick animation. So the light passing to the device is changed in its phase through the different optical path difference, depending on the state of the deformable membrane. And the deformable membrane is changed by electrostatic actuators that are embedded within the device. And that gives you higher contrast, better resolution for your optical device. And here I explain the working principle in a schematic. Depending on which electrodes you turn on, this deformable membrane is pulled and pushed in a different direction. And you can also do push actuation because you have an incompressible liquid involved. From a perspective of a component, we are somehow between tunable and adaptive lenses and deformable mirrors with respect to the degrees of freedom. And we managed actually to build with the device the smallest AO microscope in the world, where you have just an objective, beam expander, and our device inserted here. And we already received very impressive results with 1 micrometer fluorescence beads, and we call it the smallest AO microscope in the world. And you see there's actually no wavefront sensor also necessary, because that particular functionality we implement with a technique called wavefront, sensorless wavefront estimation. We managed also to solve an old nuisance of optofluidic devices, namely gravity neutrality. That means we can use our device in both horizontal and vertical orientation, and we solved that with a smart system design and being able to compensate for exactly the aberrations that are induced by gravity up to the 8th order of radial Zernicke modes. You can also put multiple of these devices in a sequence. You can make cascading elements. We demonstrated that here with 2 of our devices with different actuator layouts, and we could actually use one as a woofer, the other one as a tweeter with a low and high order correction performance. That actually made it to the title page of SPIE News very recently. Happy about that. The technology as generic optical component has multiple fields of applications. I already talked about microscopy, but you can also talk about ophthalmology, where you can think of more compact devices, or about material science and semiconductor inspection, or getting a device in a compact 3D micro nano printer. The same goes for AR or even amateur astronomy. So it's a very broadly applied technology. And with our first minimum viable product, we call the Delta 7. We want to enter the market later this year. It's a DPP-based wavefront modulator, a phase modulator with 63 actuators. And we are currently looking for early access customers from industry and research. We are growing, so we are offering a few opportunities for interested candidates, or if you know someone, I would be happy to receive an application. And I want to thank all our sponsors and also our member as member of EPIC. We actually answer those 2 questions, and we are always interested in new use cases and also scaling the manufacturing. And if your optical system suffers from aberrations, particularly if there are dynamic ones, non-static ones, I would be welcome to have a discussion with you. Thank you very much for your attention.